Hello, I am Avirup Saha, a PhD student of the Indian Institute of Technology, Kharagpur, and my advisor is Professor Niloy Ganguly. In this video, I will present my thesis, which is titled Modeling Self-Reinforcement and Intercompetition in Multivariate Temporal Point Processes and Graph-Based Semi-Supervised Learning. This is the outline of my thesis. In Chapter 1, we will introduce the subject matter. In Chapter 2, we will discuss modeling, self-reinforcement, and intercompetition in multivariate temporal point processes. In Chapter 3, we will try to understand the success of graph-based semi-supervised learning using partially labeled stochastic block model, which is a network generative model. In Chapter 4, we will explore safe graph-based semi-supervised learning by modeling self-reinforcement and intercompetition of communities. In Chapter 5, we will conclude this thesis and present some directions for future work. We now come to the introduction of the thesis. This is what a multivariate temporal point process looks like. It consists of a set of processes which are roughly overlapping in their time window, and each process consists of a series of discrete events localized in continuous time. In this thesis, we add magnitudes to events. An event magnitude denotes the strength or the intensity of the event which is occurring at the particular time. In case of a product review stream, the event would be the posting of a review of a product, and the event magnitude would be the review rating. In a network packet stream, the event would be the emission of a packet, and the event magnitude would be the packet length. In a hashtagged tweet stream, the event would be the posting of a tweet bearing the hashtag, and the event magnitude would be the retweet count of the tweet. This illustrates the reinforcing effect of product review ratings. If a product reviewer gives a 5-star review for a product, this will lead to higher sales and it will induce more users to buy that product and post reviews. This illustrates the reinforcing effect of retweet counts. Due to the image content of this tweet, it was retweeted 3 million times. This led to high visibility of the hashtag Oscars and also led to more tweets bearing this hashtag. This illustrates the negative reinforcing effect or the inhibitory effect of network packet lengths. This occurs because of a fixed bandwidth delay product. Therefore, if a host is transmitting large packets, it can transmit less, and if a host is transmitting small packets, it can transmit more. This illustrates the effect of inter-process competition. Since products and hashtags compete for limited user attention, while network hosts compete for limited bandwidth, when one of these processes gains in intensity, the other competing process will lose in intensity and vice versa. This illustrates the effects of self-reinforcement and intercompetition at the community level in graph-based semi-supervised learning. While determining the label of an unlabeled node, labeled nodes belonging to the same community will reinforce each other, while those belonging to different communities will compete against each other. In this case, the nodes belonging to the blue community are dominating over the nodes belonging to the red community while determining the label of this unlabeled node. In this case, the nodes belonging to the red community are now dominating over the nodes belonging to the blue community. Now we come to the major contributions of this thesis. In Chapter 2, we give two template models, RNN-TPP and RNN-GAN-TPP for multivariate TPPs. And then we see how these models can model the effects of self-reinforcement and intercompetition at the process level. In the next chapter, we give a concrete analysis of the success and failure of graph-based semi-supervised learning, especially label propagation on the partially labeled stochastic block model or PLSBM. In Chapter 4, we provide a novel concept of GLM safety to compare two graph-based semi-supervised learning algorithms on the basis of guaranteed performance on the graph latent model or GLM. We also give a novel GSSL algorithm called Class Sensitive Expander or CSX, which incorporates self-reinforcement and intercompetition at the community level. We also demonstrate the superior GLM safety profile of CSX compared to the well-known label propagation and expander algorithms. Now coming to chapter 2. In this chapter, we will try to model the self-reinforcement and intercompetition effects in multivariate temporal point processes. This is the outline of the chapter. We will first commence with the model. In this thesis, we present two template models, RNN-TPP and RNN-GAN-TPP. Both of these models are based on RNNs, whereas RNN-GAN-TPP incorporates a generative adversarial network or GAN. This is the block diagram of the architecture of RNN-TPP. It consists of three layers: the input layer, the hidden layer, and the output layer. It takes as input ground truth timestamps and event magnitudes and generates the intensity of the process. It is trained by minimizing the negative log likelihood as well as the ranking loss. Here we take a closer look at the input layer of RNN-TPP. The input layer is a simple linear transformation from the ground truth timestamp. In the hidden layer of RNN-TPP, we take the output of the input layer and combine it with the ground truth event magnitude. This event magnitude is a distinctive characteristic of our models, which actually enables us to model the effect of self-reinforcement. This parameter beta I is a learnable parameter, and this will be positive in case of the self-reinforcing effect. For example, the effect of retweet counts on hashtag diffusion in Twitter and the effect of review ratings on product popularity in e-commerce. On the other hand, this parameter will be negative in case of the self-inhibitory effect. For example, the effect of packet lengths on packet emission patterns of a network host. This is the output layer of RNN-TPP. This layer takes the input of the hidden layer as well as the last observed timestamp and generates the conditional intensity of the process. This is the block diagram of the architecture of RNN-GAN-TPP. It consists of a generator and a discriminator. These are trained in an adversarial manner. While the generator generates fake sequences, the discriminator will take the fake sequences from the generator and the ground truth sequences and determine which is real and which is fake. This is the input layer of the generator. It is similar to that for RNN-TPP. This is the hidden layer of the generator. Once again, it is similar to that of RNN-TPP. This is the output layer of the generator. This is slightly different from the output layer of RNN-TPP. While this also generates the conditional intensity lambda I, it also generates the conditional density function Fi. Using this conditional density function, it generates the next timestamp in the sequence Ti plus 1. Moreover, it also generates the next event magnitude in the sequence Ki plus 1 using an autoregressive model which takes as input the current event magnitude Ki as well as the current conditional intensity lambda I. This is the discriminator of RNN-GAN-TPP. It is a two-layer RNN where the final layer is a sigmoid which outputs the probability that the input Ti and Ki which are coming into the discriminator belong to the real sequence. It is to be noted that this discriminator can take both the output of the generator as well as the ground truth event magnitudes and timestamps as input. This is the ranking model we use to capture the competitive relationship between the processes. We split the time window into L equal sized intervals and compute two quantities. This quantity y comes from the ground truth, whereas this quantity delta comes from the model. So based on y and delta, we compute 4 ranking losses: an unbiased loss, or loss based on recall, a loss based on precision, and a loss based on AUC. Coming to the inference of our model, for inferring the parameters of RNN-TPP, we maximize the log likelihood, which is obtained directly from the conditional intensity of the process. For the inference of RNN-TPP with the ranking model, we minimize the negative log likelihood combined with the ranking loss. We have slightly different forms of the ranking loss for 2 sets of measures, one for precision and recall, and one for unbiased and AUC. For inferring the parameters of RNN-GAN-TPP, we first obtain the generator log likelihood, which is similar to that of RNN-TPP, and then we also obtain the discriminator log likelihood. This consists of 2 parts: the log likelihood over the real sequence coming from the ground truth, and the log likelihood over the fake sequence coming from the generator. Then we combine these to generate the adversarial loss, and this adversarial loss is similar to the standard adversarial loss used in generative adversarial networks. Finally, we obtain a minimax optimization problem for RNN-GAN-TPP, where in addition to the adversarial loss, we have a term for the negative log likelihood. Similarly, we perform the inference of RNN-GAN-TPP combined with the ranking model. It is similar to that for RNN-TPP, except in this case we have an adversarial loss and a min-max optimization problem. Again, the form of the ranking loss is different for these 2 groups of measures. Now let us discuss an application of RNN-TPP to product popularity prediction. In this case, RNN-TPP has been called the competing recurrent point process, or CRPP. We use product review ratings as the event magnitudes Ki, and RNN-GAN-TPP is not deemed necessary for this task due to the sparsity of the temporal patterns of product reviews. We used 6 Amazon review datasets, and each dataset was related to a class of products. We have smartphones, laptops, refrigerators, washing machines, ACs, and TVs. These are the results in product popularity prediction. Here, the performance is measured in terms of the mean absolute percentage error, or MAPE, and our model CRPP performs the best among all the baselines. These are the results in product rank prediction. Here, the performance is measured in terms of the Spearman's rank correlation coefficient, or SRCC, and CRPP, our model, performs the best among all the baselines. These are the results for the variance of CRPP created by varying the ranking loss measure used in the model. We see that for the experiment with MAPE, precision and recall turn out to be the best measures, whereas in the experiment with SRCC, AUC in general gives a good performance. Now we come to an application of RNN-TPP to network traffic prediction. In this case, RNN-TPP has been called the network transmission point process, or NTPP. We use network packet lengths as the event magnitudes, and RNN-GAN-TPP was not deemed necessary for this task due to the high predictability of the temporal patterns of the network packets emitted by a host, and this phenomenon has been referred to as self-similarity in network traffic modeling literature. For conducting our experiments, we use 2 different types of datasets. We collect data from 4 cyber defense exercises. These exercises are carried out in a simulated environment where one team generates network attacks on the system and the other team tries to defend the system from those attacks. We also have 3 real-world datasets. World Cup 98 is a server log dataset coming from the official servers of the Football World Cup in 98. UNIDC is a university data center dataset, and SNE with Torrent is a peer-to-peer network dataset. These are the results in host traffic prediction. Here, the metric of evaluation is MAPE, and our model NTPP performs the best among all the baselines. These are the results for host rank prediction. Here, the metric of evaluation is SRCC, and once again, our model performs the best among all the baselines. These are the results for the variance of NTPP created by varying the specific type of ranking loss used in the model. For MAPE, precision and recall perform the best, whereas for SRCC, in general, AUC gives a good performance. Next, we come to an application of RNN-GAN-TPP to hashtag popularity prediction. In this case, RNN-GAN-TPP has been called the hashtag GAN process or HGAN-PP. We use retweet counts as the event magnitudes, and RNN-GAN-TPP was deemed necessary for this task due to the burstiness and unpredictability of hashtag use trends. We experiment on 7 datasets, each consisting of tweets bearing a group of hashtags related to a real-world event. These events are Oscars, the Big Billion Day sale of Flipkart, the MTV Awards, the Copa America football tournament, the Democratic primaries for the US presidential election, the ICC T20 Cricket World Cup, and the earthquake in Nepal in 2015. These are the results for hashtag popularity prediction. Here we measure the performance in terms of the mean absolute percentage error or MAPE. And here our model HGAN-PP shows the best performance among all the baselines. Here we consider the performance of hashtag popularity prediction on 2 representative datasets, Nepal earthquake, which contains stable temporal trends, and BBD, which contains bursty temporal trends. We see that the performance graphs for the models are relatively close together in case of Nepal earthquake, but they are relatively separated in case of BBD, and therefore we conclude that HGAN-PP offers greater advantage over baselines for bursty data. Here we perform an ablation study on the different components of our model. The HDR version of our model contains only the effect of the retweet counts and therefore models only the effect of hashtag tweet reinforcement. The IHC version of our model contains only the effect of the ranking loss and therefore models only inter-hashtag competition, whereas the generic version of our model contains neither of these two effects. Here we see that the IHC version of our model in general performs better than the HDR version of our model. However, the full model, namely HGAN-PP, performs better than either of them. Therefore, we conclude that the effects of hashtag tweet reinforcement and inter-hashtag competition are additive, but inter-hashtag competition is relatively stronger. These are the publications from this chapter. Now we come to chapter 3, which is called Understanding the Success of Graph-Based Semi-Supervised Learning using Partially Labeled Stochastic Block Model. This is the chapter outline. We will first give a brief background, and then we will discuss the concept of failure of recovery, which gives an upper bound on accuracy. We will give the condition for exact recovery, which is 100% accuracy. And we will also discuss the concept of partial recovery, which gives a lower bound on accuracy. And then we will give some empirical results. Now let us jump into the background. This is discrete label propagation, which was proposed by Yamaguchi et al. In Ichikai 17. It is similar to ordinary label propagation, except that the optimization is performed on the discrete space, whereas ordinary label propagation performs optimization on the continuous space. Here we describe the partially labeled stochastic block model or PLSBM as defined by Yamaguchi et al. In Ichikai 17. PLSBM is characterized by 5 parameters: n, which is the total number of nodes, nl, which is the total number of labeled nodes, alpha, which is the label noise parameter, capital K, which is the number of communities, and capital Q, which is the assortativity matrix. This defines a generative model over a family of partially labeled graphs as follows. It consists of three separate models: a membership generative model, an adjacency matrix generative model, and a label generative model. The membership generative model assigns a label to each node I from 1 to n. The label xi corresponds to the community membership of the node, and this label is assigned with uniform probability 1 by k, yielding a set of balanced communities in expectation. In the adjacency matrix generative model, the entries of the adjacency matrix A are generated independently, with the probability of the ijth element being 1 being equal to the xijth element of the associativity matrix Q, where Q is a k by k symmetric matrix where each entry is a real number between 0 and 1. In other words, Aij is drawn from a Bernoulli distribution with parameter Qxi xj. In the label generative model, for the first NL nodes, which are labeled, potentially noisy labels xi prime are revealed IID as follows: the probability of the revealed label being equal to the true label is equal to 1 minus alpha, and the probability of the revealed label being equal to any one of the other labels is equal to alpha by k minus 1. The rest of the nodes indexed nl plus 1 to n remain unlabeled. This is an illustration of the effect of the associativity matrix Q in SBM with three communities. If the diagonal entries are dominant, it will generate a homophilic network. If the off-diagonal entries are dominant, it will generate a heterophilic network. If the entries of Q are random, then it will generate a random network. And if the entries of Q follow a specific pattern, it will also generate a tree type of network. Yamaguchi et al. Posited the equivalence of the solution of a DLP and the maximum a posteriori solution of a PLSBM under certain conditions. Here we provide a summary of our contributions. Similar to Yamaguchi et al., we also provide an equivalence guarantee, but we use a slightly different version of PLSBM where the node labels are generated stochastically. We give a failure guarantee, which provides an upper bound on accuracy, and we provide two types of success guarantees: one where the accuracy is lower bounded by some value, and where the accuracy is guaranteed to be 100%. We provide proofs for exact recovery and failure of recovery, while only proposing a conjecture without proof for partial recovery. Now we discuss failure of recovery, which gives an upper bound on the accuracy. Now we present the theorem on failure of recovery. This theorem states that if the quantity d Bern max q, which is defined as the maximum KL divergence between the diagonal and the off-diagonal elements of Q, is upper bounded by this quantity, which is a function of delta, then every algorithm will fail to estimate the true membership X with the probability of error more than delta for any given delta in 0 to 1. From here we can directly draw a corollary on an upper bound of the accuracy of label propagation. And we note that this is a sufficient condition for the upper bound. Now coming to exact recovery, which gives 100% accuracy. We provide accuracy guarantees for label propagation in three distinct regimes of two-community PLSBM as defined by Yamaguchi et al. Based on label volume and quality. We consider a rare regime where there are very few labels. Then we consider an abundant but non-informative regime where there are adequate labels with around 50% label noise, where labels are equiprobably correct and incorrect. This means that the information content of the labels is low. Thirdly, we have an abundant and informative regime where we have adequate labels with either very high label noise, that is, labels are almost always incorrect, or very low label noise, that is, labels are almost always correct. In both cases, the information content of the labels is high. These are the formal definitions of these three regimes. Now we present a theorem on exact recovery. It states that if maximum likelihood estimation exactly recovers the true community membership, then any one of these three conditions must be satisfied, where each condition corresponds to a specific regime. And from there, we can directly draw a corollary on the 100% accuracy of label propagation. We note that this is a necessary condition. Now we come to partial recovery, which gives a lower bound on the accuracy of LP. Here we would give a conjecture on partial recovery. It states that if the maximum likelihood estimate makes at most a certain number of mistakes, asymptotically and with high probability, then any one of these three conditions must hold, each condition corresponding to a specific regime. These conditions are similar to the conditions we saw earlier, except for the scaling factor of log n by s and the limit infimum as n tends to infinity. From here we can draw a corollary on the lower bound of the accuracy of label propagation. We note that once again this is a necessary condition. Now we come to the empirical results. Here we demonstrate the effect of the success and failure conditions. Failure of recovery is represented by the red regions where the accuracy is at most 50%. Exact recovery is represented by the green regions where the accuracy is guaranteed to be 100%. And partial recovery is represented by the regions which are left demarcated by the dashed vertical lines where the accuracy is at least equal to the indicated value. For instance, the accuracy in this region is at least equal to 99%. We have three different graphs for the three regimes of PLSBN. Here we investigate the effect of model parameters on the failure condition. We see that if we keep the number of nodes n fixed and vary k and epsilon l, then while LP succeeds for a small value of k, it fails for a large value of k, and the accuracy drops in a hyperbolic curve, and the nature of the curve is guided by the value of epsilon l. Conversely, if we keep k and epsilon l fixed and vary n, then we see that in a particular case, although for a small value of n, LP might be in the failure regime, but by increasing n, we can bring LP to the success regime. And all these effects can be explained directly by investigating the theorem on the failure of recovery. This is the publication from this chapter. Now coming to chapter 4, where we shall explore safe graph-based semi-supervised learning by modeling self-reinforcement and intercompetition of communities. Here we give an outline of the chapter. We shall first discuss the setting of GSSL. Then we shall discuss the partially labeled graph latent model or PLGLM. We shall then discuss some generalization bounds. We then give a notion of GLM safety and they finally provide some empirical results. Coming to the setting of GSSL. Here we describe the setting of GSSL. AY prime is a partially labeled graph with an n by n adjacency matrix A and a partially revealed label matrix Y prime, and Y star denotes the true label matrix indicating the community membership. The labels are one-hot encoded. That is, in a two-class setting, labels can either be 0, 1 or 1, 0, and we denote these by E1 and E2 respectively. All zeros indicates an unlabeled node. Let us define a diagonal matrix capital S such that the ith diagonal element is 1 if the ith node is labeled and the ijth element is 0 in all other cases. We also define a prior over labels U, and typically this is a uniform prior. Here we give the Jacobi iteration versions for label propagation and expander. We see that expander differs from label propagation in the uniform prior term. Here we present our novel GSSL algorithm called class-sensitive expander, or CSX. It includes a novel link penalty term W, where Wij is +1 if nodes I and j are labeled and belong to the same class, and -1 if they are labeled and belong to different classes. Otherwise, Wij is 0. We say that W acts as a pseudo-adjacency matrix with positive and negative edges. Here we give the Jacobi iteration version of our algorithm. This differs from expander only in the link penalty term W, and we see that W is on the same level as the adjacency matrix A, and therefore we call this W a pseudo-adjacency matrix. Here we see the effect of the link penalty term W. It inserts positive and negative pseudo edges in the graph. We say that the positive edges correspond to the self-reinforcement effect and the negative edges correspond to the intercompetition effect. Here we demonstrate the effect of self-reinforcement. In this original graph, it is unclear what should be the inferred label on this unlabeled node because of equal influences from the blue and red communities. However, after inclusion of the positive pseudo edges, the inferred label on this node becomes red. Here we demonstrate the effect of intercompetition. This unlabeled node is directly connected to two nodes of the red community. However, each node of the red community is connected to two more nodes of the blue community, and therefore its effect is weakened and the label is ambiguous. However, due to addition of negative pseudo edges, these nodes of the blue community get separated out, and finally the inferred label on this unlabeled node becomes red. Here we present the optimization objective of our GSSL algorithm, and the link penalty term is included here. Coming to the partially labeled graph latent model, or PLGLM. Here we define PLGLM. It is characterized by parameters n, which is the total number of nodes, script x, which is the domain of the latent vectors, epsilon L, which is the label revelation probability, f, which is the homophily function, PE1, which is the distribution of the latent vectors of the first community, which is labeled by E1, and PE2, which is the distribution of the latent vectors of the second community, which is labeled E2. This defines a generative model over a family of partially labeled graphs with the following properties. Firstly, the classes must be balanced. That is, the true labels Y star must satisfy this property, that is, the classes must be equal sized. Secondly, there has to be a latent vector generation model. That is, for node I, a latent vector xi will be sampled from the distribution pyi, which can either be pe1 or pe2 depending on the label of the ith node. Thirdly, there will be an edge generation model. That is, for each node pair ij, the edges ij of the graph will be drawn from a Bernoulli distribution with parameter f xi xj, where f will be the homophily function that must satisfy the symmetric property, that is, f xi xj must be equal to f xj xi. Lastly, there is a label revelation model. Here, for each node, the labels y prime are revealed from the underlying labels y star, such that y I prime, that is the revealed label of the ith node will be equal to 0 with probability 1 minus epsilon L, and yi prime will be equal to yi star, that is the ground truth label, with probability epsilon L. Therefore, we assume no noise in the revealed labels. Next, we discuss the generalization bounds. Here we give a sufficient condition for a lower bound of the accuracy of our algorithm CSX on PLGLM. Here we introduce two new quantities, P and Q. While P is the intra-cluster edge probability, Q is the inter-cluster edge probability. Therefore, this quantity P minus Q represents the homophily of the graph. We propose that if this condition holds, then our algorithm CSX is guaranteed to achieve at least 101 minus s by n% accuracy on PLGLM. Since our algorithm CSX is more general than both LP and expander, by suitably setting the values of some parameters, we can also derive the sufficient conditions for at least 101 minus s by n% accuracy for both of these algorithms on PLGLM. Here we show the algorithm specific bounds for all three algorithms. We see that by defining some constraints on the parameter values of gamma 3 and lambda, we are able to determine the sufficiency conditions for LP and expander. We also note that the sufficiency condition for CSX has an additional epsilon L square term on the left-hand side. This term will become significant as we shall show in our empirical results. Coming to GLM safety. In order to study GLM safety, we define the parameter space under PLGLM where an algorithm A has a guaranteed accuracy of 1 minus s by n. We call this parameter space omega. While omega depends on a number of parameters, namely y star, that is the ground truth labels, epsilon L, which is the label revelation probability, the algorithm A, and the number of mistakes s, we keep y star and epsilon L constant so that omega becomes a function only of A and S. Next, we define a notion of GLM safety. We say that an algorithm A1 is GLM safer than algorithm A2 for a given accuracy 1 minus s by n if omega of A2 and S is a subset of omega of A1 and S, with all else remaining fixed. For sufficiency bounds of the form considered in this paper, we have derived a form for the cardinality of the set omega of A and S. And we have seen that for determining the subset relation, it is sufficient to compare the cardinalities of the sets. Next, we posit a theorem that CSX is GLM safer than LP and expander. The condition that we require is that epsilon L, the label revelation probability, is greater than a specific value epsilon LC, where epsilon LC is governed by S, which is the number of mistakes, and N, which is the number of nodes. We call epsilon LC the crossover point, and this is actually a conservative estimate of the crossover point. Here we show the theoretical values of the crossover point epsilon LC for different values of the guaranteed accuracy, as well as for different values of the number of nodes n in the graph. Here we see that the crossover point typically tends to increase with the increase in the level of guaranteed accuracy, and also tends to decrease with increase in the number of nodes n. Therefore, for large enough graphs, CSX will always offer a theoretical advantage compared to LP and expander. And here we have to give a disclaimer that these values are only valid for two community graphs sampled from PLGLM and may not be applicable for real-world graphs in general. Next, we show the empirical results. This is our instance of PLGLM. We generate graphs with 300 nodes using a two-dimensional latent space. We generate latent vector distributions for the two classes using two-dimensional Gaussian distributions with means plus minus mu and a fixed variance sigma square I. The homophily function is said to be the Gaussian radial basis function. Here we show the performance of a CSX as a function of the norm of the mean mu, the standard deviation sigma, and the label revelation probability epsilon L. We have demarcated the regions of guaranteed accuracy of CSX for different values of accuracy. Here we see that as epsilon L increases, these regions also correspondingly increase in size. Here we compare the performances of CSX and LP. We have demarcated the regions of guaranteed accuracy for both the algorithms. While CSX does not always outperform label propagation for all these settings, but the regions of guaranteed accuracy of CSX are clearly larger than those for label propagation at high values of epsilon L. A similar conclusion can be drawn for the expander algorithm since LP and expander share the same sufficiency condition. Next, we show some experiments on real-world graphs. We have sampled 4 graphs, G1 through G4, from 3 real-world datasets. We have chosen different combinations of class balance and the homophily estimate p hat minus q hat, where p hat denotes the intra-cluster edge probability and q hat denotes the inter-cluster edge probability. In our algorithms, we have used a uniform prior for balanced classes and a non-uniform prior for unbalanced classes. These are the latent space visualizations in 2 dimensions of these 4 graphs. In graphs G1 and G2, due to high homophily, the communities are clearly demarcated. But in graphs G3 and G4, due to low homophily, the communities are overlapping. Here we show the performance of CSX, LP, and expander on real-world graphs G1 through G4. In graph G1, which is balanced with high homophily, all 3 algorithms perform reasonably well. However, at low values of epsilon L, LP and expander suffer from a problem called label flipping, where they tend to flip the labels of the revealed nodes. However, due to the presence of the link penalty term in CSX, CSX is robust to this effect. In graph G2, which is unbalanced with high homophily, CSX and expander perform roughly similarly. However, due to the absence of the non-uniform prior, the performance of LP suffers. In graph G3, which is balanced with low homophily, LP and expander perform roughly similarly. However, CSX is superior to both these algorithms. This is the effect of the epsilon L square term in the left-hand side of the sufficiency condition for CSX. Due to the presence of this term, CSX not only gains a theoretical advantage, but it also gains a very distinct empirical advantage, as we see here. This term becomes significant in the balanced case because the value of p minus q is low, and therefore the epsilon L square term becomes significant. In G4, which is unbalanced with low homophily, the non-uniform prior dominates, and naturally this hurts the performance of LP. However, the effect is far more pronounced in this case than in the case of G2. This is the publication from this chapter. Finally, we come to the conclusion and future work. In conclusion, we have shown that self-reinforcement and intercompetition are a recurring theme across these seemingly disparate domains of multivariate TPPs and GSSL, and modeling these effects can lead to superior performance as well as better theoretical guarantees of success, as we have seen in case of GSSL. These are our contributions to the theory of multivariate TPPs. We claim that RNN-TPP and RNN-GAN-TPP offer simple and elegant solutions to the problem of modeling multivariate TPPs involving these two effects of self-reinforcement and intercomputation. We propose the ranking model as a simple and scalable alternative to the conventional approach of cross-covariance analysis, while RNN-TPP is sufficient for the product review streams, which have sparse patterns, and network packet streams, which have predictable patterns. RNN-GAN-TPP with the adversarial GAN framework is useful for modeling the bursty and unpredictable temporal patterns of hashtag flow. These are our contributions to the theory of GSSL. We have built a bridge between the hitherto disparate domains of GSSL and network modeling, building upon the foundation set by Yamaguchi et al. In HGI 17. We have also provided concrete and quantitative interpretations of the notions of success, failure, and safety of graph-based semi-supervised learning, while previous works, including Yamaguchi et al., provide only a vague qualitative treatment. This is our future work in TPP domain. We can investigate the effect of network structure on multivariate TPPs, where each node emits a process. And while we have not performed any theoretical analysis of TPPs due to the supervised setting, but this may become necessary in a semi-supervised setting. This is our future work in GSSL domain. We can study the effect of label noise on the accuracy bounds of GSSL algorithms on PLGLM. We can investigate broader families of real-world graphs where the assumptions made by GLM may not necessarily hold. We can also extend the concept of GLM safety to other well-known GSSL algorithms such as adsorption, modified adsorption, edge-explained, etc. by theoretically characterizing their performance on PLGLM. These are the publications from the thesis. We have 1 journal and 5 conferences. Thank you.